Yeah, good afternoon, madam. No, your voice is not audible. Excuse me. I'm not able to hear a voice. No, are you able to hear my voice? Are you able to hear my voice? Good. No, your voice is not audible for me.
Yes, clear.
Yeah. Now fine.
Respected dignitaries, your professors, esteemed guests, and dear students, a very good afternoon to everyone. It's great to have you all back after lunch. I hope everyone enjoyed their lunch and kindly request everyone to settle back into your seats. After having any, sir, are we audible to you, sir?
Yes, now fine. Yes, yes. Please go ahead.
Oh, okay, sir. Thank you, sir. After having an insightful session on net zero industry innovation and strategies for industrial pollution control, we are here for yet another illuminating session. I, Vandana Lakshmi, and myself, Harshita Kadri, a final year undergraduate from the Department of Chemical Engineering, take the honor of welcoming you back. Before moving on to the second section, I want to ask if you ever wondered how we can purify water using naturally occurring materials without generating harmful byproducts, and how large scale models evolve into large scale industrial applications? If yes, appreciate yourself, and if that's a no, don't worry, we got your back. To guide us through this fascinating topic, we are honored to have with us a distinguished expert, Dr. Sarvarajan Narayan Garu, Associate Professor in the Department of Biosciences and Bioengineering at Indian Institute of Technology, Guwahati. It's my absolute privilege to introduce you to this incredible journey one that has been into the expert series today. Dr. Sarvarajan Narayan Garu has done his PhD in Chemical Engineering from the Indian Institute of Technology, Madras, and postgraduated in Chemical Engineering from AC College of Tech, Anna University, and graduated in Chemical Engineering from Annamala University. Previously, Dr. Sarvarajan Narayan Garu worked as an assistant professor in the Department of Chemical Engineering, NIT Calicut, and joined IIT Guwahati as an assistant professor and further got advanced as associate professor. He's been a principal investigator in 11 sponsored projects, which include experimental and numerical investigation of reactive extraction and phase transfer catalysis in a microfluidic system under Kerala State Council for Science, Technology and Environment. And he's a part of ongoing project development of an integrated wastewater treatment and food production system using ceramic membrane and microscopic reactors under the Department of Science and Technology with a grant of INR 68.92 lakh. Dr. Sarvarajan Samigaru has won 32 publications and 5,862 citations to his name and has an H index of 43 and an item index of 101. Under his guidance, there are 17 completed PhDs and 12 ongoing PhDs. His distinguished accomplishments include receiving the Research Council Grand Challenge Award 2022 from IIT Guwahati, the Hiroshi Think of Ecology Award 2016 from Hiroshi Corporation, Japan, and the Kerala State Young Scientist Award 2014 from the Kerala State Council for Science, which carries a startup research grant of rupees worth 50 lakhs. With this advocate, he has received a total of 7,50,000 for publishing 50 articles in peer-reviewed SI journals. He has also received National Doctoral Fellowship from 2006 to 2009, which is a prestigious and highly valued scholarship given by the All India Council for Technical Education to the top 50 research scholars in India. He's been an editor for prestigious journals Springer Nature and Elsevier, two of the leading global academic publishers, and with extensive expertise in the peer review process, scholarly writing, and journal management, he plays a pivotal role in shaping the dissemination of high quality research across various fields. Today, we have him with us to deliver a lecture on water purification technologies using biomaterials from lab scale to pilot scale. Please join your hands together to welcome Dr. Sarvarajan and Sani Garu to educate us with the topic. I request you to take over from here now, sir.
Yeah. So can I start now?
Yes, sir. Yes, sir.
Yes. Okay, great. Yeah. So are you able to see?
Yes, sir. Yes, sir.
Everything slides are moving?
Yes, sir. Yes, sir. They are moving, sir.
Okay. Yeah, good afternoon all. Once again, thank you for a very brief introduction. First of all, my special thanks to Professor Devi from your university. She keep on called me, and I think it was wonderful because the way she approached me and even the all details she shared with me. I think thank you once again, madam. Today I'll be delivering for water purification technology using biomaterial from lab scale to pilot scale. Mainly, our research interest starts with the first. Yeah, it's fine. Are you able to hear my voice?
Yes, sir. Yes, sir. We can
Yeah.
hear you, sir.
Yes, yes. So our lab works different type of area here. First, start with the wastewater bioremediation. It's basically involves adsorption, then biosorption, then packed bed column studies, then AOP, advanced oxidation process. We have different students are there. They are all in the PMRF. The Prime Research Fellowship. They're getting like 80,000 fellowship plus 2 lakhs grant from the individual project they're working. So then I also worked as a microfluidic reactor. Basically, this study with the environmental, the scale level different. Another one is for air pollution, air modeling. This normally it's only completely computational works. But today mostly I talk about the absorption, then microfluidics, then how we are integrating all the system inside. So the basically the novel absorbent we have to develop with this one. Why you want novel absorbent? Because it's always give good absorption capacity. So we are targeting these are main pollutants, dyes, and then heavy metals, antibiotics, and rare elements. Example like the Tamil Nadu, Tirupur is heavily the dyes pollution is are there. And if you take heavy metals, especially in the IIT Guwahati located to near Brahmaputra River, from what we found that the heavy metals, especially the arsenic contaminates more in the Brahmaputra river water. Of course, this the North India, especially the Ganga, most of the rivers are there. We used to test for most of the rivers, but we found that the heavy metal arsenic more in the Brahmaputra water. Then antibiotics. This mainly because of after COVID, everyone started to use antibiotic and simply they're discharging to water body. Then how we have to remove this also. Then finally we come to rare earth elements. It's mainly it's mining activities. This one we deal here rare earth elements, cerium power. This one. So totally the four how we are going to treat with the absorption. Then we'll take it to industry level scale. So once everything done and we have the toxicity studies. So this even we can call as a plant doctor. One of the Professor Langraj Sahu is here. So we always after testing this one, then we'll go to test the different type of toxicity studies, like seed toxicity studies and then microbial all. So finally we come up with this one is the like our discharge the evidence one. So before start this one, say example you want to take some novel absorbent, especially in IIT Guwahati, it's a very beautiful campus compared to all over India. I don't know there are a lot of visited. It's one of the beautiful campus. It's a completely greeneries. So you take some plant biomaterial and take it and make it a powder. After making powder, then that's look like novel adsorbent. So our novel biosorbent. Then basic characterization we have to do this one. Say example SEM, PEM, then XRD, FTR. These all basically all tests we have to do. Once everything done and we get some idea whether this is physically the absorbent is good or we are able to achieve that as good surface area. So many things from there we can find it this one. So once this done, then we have to go batch experiments. So the batch experiments very simple. You do initial pH studies, then you take some biosorbent or adsorbent, then how much dosage you are going to give, how much concentration or what is temperature. So once everything done, then we can move to packed bed column. So this is a very batch level. If batch level get a success, then we can move to packed bed column. Once a packed bed column success, then we can move to always industry level. So everything done, then after that, of course, we have to go for these studies, sea toxicity studies, a different type of this one. So overall picture of our this one. So you take activated carbon, and then these are basically two type of modification. One is a physical modification, other is a chemical modification. So the physical modification, you take any biomaterial and then you heat up that one. Then physically you modify with the temperature this one. But chemically modification meaning you want to add something, some compound physically, chemically, then automatically you can enhance the absorption capacity. But I don't discuss too much this one. So basically take activated carbon and then we have done some this one. But finally the activated carbon now chemically modified activated carbon is available. And once done, of course, you have to do the SEM and TEM, whether it is really porous and we are able to clearly to absorb the pollutants. Say example, we have different type of pollutants, the dyes and then other different type of pollutants are there. So how we are going to take that one? So we have to check whether this porous textures. We have to check with it before and after that one. For that purpose, this one. This I leave it because then we used to study like bonding, how the interaction, pipe interaction, hydrogen bonding all. but I'll skip this because this is very difficult to understand. So once they're done, then other one we prepared that's called anti-tech hydrogen. It's available plenty of material. Normally we'll use for raw materials like I mean it's a very easy. The cost wise is very low. Then we can always use that one as a raw material of this one, treating dyes or water is water. So anti-tech hydrogen, you take anti-tech hydrogen, then you modify the hydrogen. So this is called a surface modified hydrogen. You can see here the surface modified hydrogen. So once surface modification is done, then this is ready for your, your target pollutants. So here, what happened? We used to here the type of dyes. Start with the direct blue, then combo red, then bromophenol blue. This one. So you can see before absorption, then after absorption. So how much is the absorption removal percentage? You can see first the direct blue. So initially this one, then how we are able to achieve. So maximum we can get like 90%, 98%. So based on what type of absorption you're using, absorbent using, whether this is chemically modified absorbent or physically modified absorbent. Then we tried with this one is for full days bed. Most of the you are all chemical engineers, so you know that one. The full days bed main purpose is here. Uh, Mainly the particle get to the full days, but if you use the packed bed, the particle never get a full days. So that's the only difference between full days bed and packed bed. So we tried with the full days bed, but of course the efficiency was not that much promising. So then, of course, this the parameter whatever we got it from batch, so we have to use here to help that one. The other one is for first we started with the dyes, then same way the cerium, this one, that is one of the rare earth elements. You just hear the commercial activated carbon, then we have developed with the magnetic commercial activated carbon. So after absorption, we are able to remove cerium ions. Same way, we have to do same term, all other studies, then phytostatic studies, all different type of studies we have to do. So first we started with dyes, then here we started with, you see there are elements. Then this is a basic playing with the parameters, how the percentage removal with respect to pH. Then again, we are able to whether get a good absorption capacity or removal percentage. So basically, we have to play with a different type of variable like pH and the dosage and initial condition. But we cannot play just like that, and we have to use some optimum variables for do this one. So I will skip this also because this is again the mechanism. I will take other one. Then other part is so far we tried with this one, no? So why can't you try with the grass? Of course, our IIT Gauhati we have very the nature is it's very beautiful. I already told you same thing. So then we decided why can't take that some grass and make us a powder and make it a grass nanocellulose. Then you add some magnetization pot. Then finally this is a magnetized grass nanocellulose. So this is also ready for now absorb cerium. We can use for not only this one cerium, we can use for dyes and the same way we can use for antibiotics and we can use for other heavy metals, whatever. But we have to see the how much we are able to remove that one. And here overall we compare the same grass windows how we used it first. First we used to dye and we got this much absorption capacity. But when you use this in terms of the pharmaceutical antibiotics, then you can see here ciprofloxacin. Then we got this much absorption capacity. But when you use again cerium, how much this one? So of course this grass windows works in the cerium compared to others well and good. But again we can take even heavy metals all this one. These are different studies for sea toxicity. I will skip it because this. So far, we discussed about the batch experiments. Then why can't we do the column studies? So this packed bed column, whatever we discussed, no. So for the biosorbent, the biomaterial or adsorbent or physically modified material, you just pack it here. That's called a packed bed column. You can take any type of sample water. This called like polluted water. You can take even heavy metal polluted water like arsenics because our campus located near Brahmaputra, so always the arsenic is more compared to all other heavy metals. But our water is a little bit, purified water compared to all other places. So you can use either dye wastewater or you can use even the sample wastewater contains like antibiotics. So what are this one? The backing material, what we discussed so far, the cellulose, then grass and cellulose. No, we have done some grass and cellulose. Then we can take even the chitosan, anti-chitosan here. It's a packing material. And you can take any type of material and then you pass through the peristaltic pump, but you cannot pass directly and you have to use some packing support like this one. Then the packing material. Then through this one, then we have to measure the outside concentration. So the basically, I will repeat once again. Use any type of wastewater. It's contain heavy metals. It doesn't matter whether dyes or antibiotics, whatever this one. And this material you can use whatever physically modified material or chemically modified material, and you pass through this one, and then finally we get a pure water. Of course, if say example, if 1,000 ppm of arsenic is there, and we are able to achieve like the outside is will come like 1 ppm or 2 ppm. So the rest of things will be get absorbed in the packing material here. So this is the picture I showed you. Basically, overall chemical engineering, maybe you know a little bit the modeling simulation. So why this modeling and simulation purpose came here? Uh, See, I want to measure the concentration here at z equal to g. This we called z equal to 0 and z equal to 20 centimeter or 50 centimeter. So this is the packing material. So what is the concentration at point entry point? What is the concentration exit point? So we can measure through this some probe. There is no issue. But I want in every places. Then of course you have to do modeling. So modeling we can get each and every every point what is the exactly value. Say example, you are passing 1,000 ppm when you cross here. Initially this 1,000 ppm, but once reach here is goes to 900, 800, 500, then finally reach 100 ppm or 0 ppm. So we want to do in terms of modeling, then of course it's possible. But if you want to measure the individual concentration for individual places, then I think you have to use a lot of probe that one. So that's only modeling purpose here. So this is a equation. This we used to call a one-dimensional solid transport diffusion and dispersion equation. So of course, all of you know that this is a diffusion. This always comes from fixed first law, d of dou c by dou z. Then after integration, then we get that one. So this is the first part we call accumulation. Then other part is what is the input, then output, then the rate of whatever disappearance here. So this one is we used to call a dispersion, a fixed first law. We can say conductive diffusion, but for this one we used to call a convective diffusion. So minus of u dou c by E. So even we can say this is a dispersion. Of course, you know all dispersion is different and diffusion is different. So this contain diffusion and this contain dispersion. Is coming from fixed first law, and this is basically the transport of this one. And here, the dou c by dou t is accumulation. We want to measure that concentration with respect to time. Say, example, t, time equal to 0 minutes, and time equal to 10 minutes, and time equal to 100 minutes. So, what is the concentration? So, we can measure exactly here. The problem is here, the dou q is the solid phase concentration. So, what do you mean solid and liquid? I'll go back, then you can understand. So, when you, for example, you pass 1,000 ppm of chromium as a liquid, because the water is contain chromium, so it's like liquid phase. The liquid phase contain chromium. So this goes to directly here. Once this touch this adsorbent material, so whatever this concentration simply transfer to gas, liquid phase to solid phase. So the liquid phase concentration we used to call C, but once the liquid phase concentration goes to solid phase, we used to call it Q. So that's called a Q, dou Q by dou T. So the C called the liquid phase concentration and the Q is the solid phase concentration. So if I want to solve this equation, it's not possible because it look like A plus B equal to 1. If somebody asks you to solve A plus B equal to 1, so we cannot solve. So we can solve, but either you assume A equal to 0 and get the value of B, or B equal to 0, get the value of A, and you get a multiple number of solutions. Or what you have to do, say A plus B equal to 1, you try to bring one more equation, say 3A plus 2B equal to something. If you bring one more equation, we can solve. So the same way here, you convert in terms of Q in terms of C, and then of course it's possible to solve, then either you convert the C, the liquid phase concentration to solid phase concentration. Of course, all of you know this, you can using the finite difference, you split up and do some OD45. We can always solve this one. So this is for again boundary condition. Normally what happened here, you assume this is a packing material, or packed but packing material, and is equal to 0, but we have to use this is a boundary condition. So you can say this is a convection diffusion and this is a conductive diffusion, a fixed first law, no? So how this arrived? Say example, at concentration here entering point, it come as a liquid, and once you reach this one, this like solid diffusion. So that's a we used to write this a conductive diffusion. Then again here conductive diffusion also there. Once you reach this point, this for at z equal to L exit, and this point, same way here convective diffusion, conductive diffusion, same way here also convective and conductive diffusion. Once you reach out, then we called as a convective diffusion. So that's only the initial boundary condition we used to call this called as a Langmuir's boundary condition. So what happened? This use here and modify this equation, then basically you have to solve. It's a very easy. It's not very tough. This one. So so far we done with this one, and then why can't you try with the recycle mode? This is called always. See, example, if you do straight through mode, the efficiency wise it's always less compared to recycle mode. Even you would have seen somewhere many places the sugar can they always pause again the sugar can juice no. So how they keep on this one then try to extract maximum juice. Same way here you do recycle of this one. Recycle meaning I'll go back. So example you are passing sample wastewater going this way then again collection again you repause again redo it. Same process continuously the exit point you connect with the inlet point. So like recycle mode. So if you do that this way, then we'll get a more efficiency for that purpose. That's only there. But the equations are almost same, but only the concentration that will change. Rest everything same. So of course we get a more efficiency compared to other one. We also solved through MATLAB, OD45. I don't know how many of them know the modeling part. So far we discussed about this one. Then we will discuss about the experimental and the micro channel, how the micro channel works. And the same principle we used for how to remove the phenol water system using this one, but it's a little costly. But why the micro channel came? So you can see the difference between the old computers and modern computers, same industries. The purpose of microfluidics why it came because when you want to produce some hazardous chemical, toxic chemical in the on-site somewhere, if you want to remote place, of course the microfluidics are very simple because you cannot take the whole industry to one place and do this one. But if you are raw material and you just make it and you get a reaction, then get a product and we can use it directly. That's the purpose of the microfluidics because we can easily handle this one. The microfluidic is always the less than 1000 microns. We used to call this always micro channel. It's always compared to batch reactor. The microfluidics reactor is we used to call it blood flow reactor. It's always give good efficiency because the surface area is very high compared to the batch reactor. And one more, always enhance the heat and mass transfer rates, and then it give for on demand for on sites this chemicals. What I just now discussed this one. It's very simple. You can take wherever you want. You can measure this one. So where example use these all the places I'll use for microfluidics. What we discussed same thing. The surface area for macro channel is very low, but if you take a micro channel very high, same here Reynolds number of course all of you know the macro channel very high, but when you use a small channel, definitely the Reynolds number is the dB rho by mu is very low. And the mass transfer here the diffusion all dominated, but when you Reynolds number is very low, then there's a diffusion dominated. Just skip it, and we can even order some micro channel from abroad, and we can even develop our own micro channel fabrication for this one. So we have done the basic material. It's called a DGBA. Then this one for and we use a T shape and Y shape channel for this one. And our sizes are normally we use 600 to 1200 microns size that one. And you can see here what is the difference between the simple for this phenol and water is there. That's called wastewater. Phenol is very toxic, and I want to remove phenol. This one. So you add dodecaine. Then the dodecaine, what happened? The dodecaine react with the phenol. Then finally we get a water. So that's the way we can remove the phenol. The phenol you want to remove the phenol wastewater. Phenol wastewater is there. You say that's the point A. Then point B you pass dodecaine, and then of course the dodecaine combination with the phenol. Then finally the water will get it. But it's a very costly with the process. But whenever if you want to use it, just I want to show an example. This one. This is a setup we used for two syringe pump, and this is a T-shaped channel and how we are done the different type of flows. We will show some videos, then you can get some ideas. And these are the syringe pump we used for do these experiments. You can see that syringe pump 1 and 2 and T-shaped micro channel, and then again camera is there and how the flow pattern is happening. Then outside this one. the select flow here, the select flow kerosene water system, and you can see here how the select flow here, and other one is for this kerosene acetic acid. Then how the color reaction changing. I don't know whether you are able to see here, and the reaction part happening at both side of select flow. This is select flow, and slowly it's a very simple reaction, not very this one. We use the kerosene acetic acid and water NaOH, and slowly how the reaction taking place from one end to other end. So this is it's a sample for how the reaction happening. Yes, I want to show you. Same thing we played with the one side with the complex nanoparticle, other side is microorganism. How the microorganism basically the cell viability, the death rate also we can measure through this one. So we tried with the batch and then of course CSTR and then microfluidic reactor. Of course, the microfluidic reactor will give very good efficient, very good this cell viability compared to others because but the problem is the costly because we cannot for large purpose we cannot use that one. But whenever you want to use for on-site production, definitely the microfluidic definitely will help us that one. Yes. So far we discussed, and then this is another problem. This is a real industry problem. Just wait. Sorry. This is basically you can see the development of integrated wastewater treatment for fuel production using the ceramic membrane microchannel reactor. See, we discussed so far microchannel and the different types of reactors or how we are going to use, but how you are going to integrate the system. That's a very important. This is basically 100 lakhs, this DST sponsored project, but we joined with the ONGC. This, of course, you are a chemical engineer, you know very well, and especially Assam have, I think you know Dibrugarh. There is a lot of oil industries are there. It starts with the ONGC, IOCL, so many industries are there, all related to petroleum industries. So we approached the ONGC and of course they discussed with us. Then they said that we have a lot of wastewater, petroleum wastewater is there. So can you treat that one and give that one? Then we said, okay, yeah, we can do that. Is not issue. So this project combination with DST, Department of Science and Technology, then ONGC, and IIT Guwahati altogether. So this one, the wastewater ONGC, they provided like 10,000 liter wastewater. Then the wastewater we pass through the ceramic membrane reactor. This is the one developed by IITG system. We developed that one. So once this pass through this one, we are able to remove all type of particles. So membrane is very simple. Nothing here. You just pass the some amount of petroleum wastewater, and finally we are able to remove all type of particle here. So once this is done, then it goes to skimmer. The skimmer job is to take oil residue from solid waste because here solid waste is there. The solid waste, then solid waste directly. The skimmer is like oil. You take completely oil residue. Then it goes to gasifier. Gasifier jobs that's burn the gas. It's called a syngas. Then we'll get a CO and a hydrogen. It's called a microchannel reactor. So what we discuss same thing. So we develop our own fabrication part microchannel. Then you pass through this one. Then we'll get a liquid fuel. This is the whole purpose. But we propose one more. The liquid fuel, the hydrogen will pass through the pass to solid oxide fuel cell. Maybe I don't know whether all of you know that one. So the solid, if you pass the solid oxide fuel cell, then we get electricity. This the whole project we used to call a zero liquid discharge. You that's a waste and so totally wasted one. Then how you are producing from waste to electricity. So this is wastewater ONGC. Maybe I'll show some live video. Then you get some idea. So the wastewater contain ONGC. Definitely, I mean the lot of petroleum wastewater is there. The ONGC produces this water. You pass to ceramic membrane reactor, particular to remove that one. Then finally go to gasifier. The microchannel reactor. What we discussed so far, it's only is work 1,000 micron, less than 1,000 micron size. So like see here, we have this one. Then we integrate a whole system. So that's the way the I mean my topic also. It starts with the lab scale to pilot scale, lab scale to through industry scale. That's the purpose one. And we developed our own our ceramic membrane reactor. You can just these are the specification for membrane reactors. And again, I just shown the picture for you to understand that one. So we have tubular ceramic membrane. How what are the areas and how much this one is this one. So this completely through automation. It works three type of mode. One is the filtration mode, and then backwashing mode, flushing mode. The filtration mode you have to run 30 minutes. Then backwashing is 1 minute. Then flushing mode is there. I will show you something you can understand. Just wait. Yes. So here, basically, the two tank is there. That the tank contains ONGC, oil and natural gas. That that wastewater, 10,000 liters they produce. So the wastewater goes to directly to. It's called a feed pump. The feed pump is the purpose is to pump the water, whatever the wastewater to pump this one. So this is called a feed pump. Then here we have 20 micron cartridge, the filter we are using here. That's meaning that whatever the above 20 micron, all will be trapped here, but only the goes to less than 20 microns only goes to other one. So once this less than 20 micron it goes to other one. This is called the 4 micron. We have different cartridge there, four different cartridge here. It goes to four different cartridge. This will always works with less than 5 microns. So most of the particle will be settled here. Once here done, then it goes to high pressure feed pump. This is because the ceramic membrane reactor we want to work that one. We have to use the high pressure pump here. The high pressure pump goes to this one through this one. Here we can see here three type of mode is there. One is the filtration mode, then the backwashing mode, flushing mode. What is the filtration mode? Because 30 minutes you continuously pause that one. Then the filtration mode works first 30 minutes. Then of course they were all membrane got choked that one. Then again you use for backwashing so that we can remove that one. So that's a flushing. And then after that, chemical cleaning also there. You pause it. This all works only within 1 minute. So it's like completely automation. So the this one the filtration, then the backwashing, flushing all works this one. Then finally we get the exit this outlet this one. So whatever we are not able to remove that one, we go back to ONG that wastewater where exactly. This is again repeat. This is 10,000 liter, 5,000, 5,000. The goes to raw water feed pump. The raw water feed pump it works only the to pump the whatever the raw water to another for this one. But again, this cartridge we are using 20 micron cartridge. 20 micron we are able to remove here about 20 micron water particle. Then after that it goes to again this less than 5 micron this one. We have four different the passing is there. So then after this works, then we have to pass through the ceramic memory reactor that works like 30 minutes filtration mode. It's a high pressure water pump. Then 30 minutes this one the works in the filtration mode. Then again if you get a membrane get a choke or something, then you use the flushing mode, backwash, all type of things. Then once everything done, then again we can do chemical cleaning. You add some we can add some even hydrochloric acid, different type of okay. Then finally, if you are able to remove this one, then again we can reuse this one. Normally, the same membrane we can use at least 10 to 15 years. This one. I hope you understand. Then another problem is this another project. We got again see that we waste water. Dibrugarh, the ONGC. I think Assam is the beauty of oil. The cost wise, if you say compared to all over India, our Assam state the petrol cost is very low because of these all most of the industries are here. And then another problem is the Brahmaputra river water. We noticed a lot of microplastics are there. Even if you take like small type of salt, in the salt also contain a lot of microplastics. But the problem is now they found a lot of research is going on. If you take microplastic, keep on this one, then even a span of 5 also getting decrease without unknowingly this one. So then this problem, why you want to do this one? So you take some wastewater, not no, sorry, you take some Brahmaputra water and pass through the raw water tank. The raw water tank contain different type of this one. One is the emerging contaminants. We used to call emerging contaminant. The emerging contaminant anion, sorry, anion, then cation, then organic pollutants. This contain like a lot of antibiotics or different type of organic pollutants. Then microplastic also here. So the first problem we worked with the wastewater, that's the petroleum wastewater. This one is a, whatever the river water, Brahmaputra river water, that water we are taking. But the river water contain lot of heavy metals and lot of even sometime. But compared to all over India, the Brahmaputra water really where we are getting near Gawati, IIT Gawati, water is good. Not that much very this one, but still they approached us. We can do this one. So then we started with same way again the own electricity we want to all. That's only the solar PV model here. So if you want pump the liquid or this one, no need to depend on others. So we get electricity from here throughout the day. So the we have to pump the water same way, and this contains all this one. Then it goes to ultrafiltration. Same. Just now I shown the live video. No, same way this works. Then we are able to achieve all type of microplastics. We are able to remove here. So microplastics use a membrane, a simple thing. Then we'll get this one. Then the same way this works a filtration mode. Then otherwise okay. Then backflashing mode, all type of mode here. Is all then after once you remove the microplastics, then this contain only organic pollutants, then anion cations. So the organic pollution we use for advanced UVC reactor to remove the organic pollutants. So once the UVC lamp using this, we remove completely for organic pollutants. Once this done, then this called the CD units. This called the electrosorption. So whatever we discuss packed bed column, no, the same way the packed bed column we are not using any electrode there, but this same principle that's called absorption and this called electrosorption. But this equipment the equipment products this Eureka Fox industry. So they this is like almost 50 lakhs. They produce this one. So basically, I think maybe you would have seen many places, even water industry, many places. The Eureka Fox one of the most dominant company for water treatment. So here that they produce this setup. Then we use this electrosorption then we use this the batch process. But whatever discussed in the some absorption, all I just put up here this one. And again, that's the way. Okay, why I want to share this one because we started with the small scale and we works with the batch and how we are moving to batch to in the industry level or bigger level. So example, this is will you 500 liter per hour get a drinking water free of all ECs, emerging contaminants. This is also same 100 lakh 1 crore sponsored project, the DST, but working with some other institutes. I work some air pollution, but I think I have another meeting, so I just because this is also some we have done some modeling part. I think I'll skip it because we measured these are air pollution measurement. You can see this Delhi, especially for Delhi is highly polluted compared to all over India. Then we work on with them. We started to measure the pollution. You can see here there is a difference between before doing experiments and after doing experiments. So then basically this is all collecting of the pollution, air pollution. The air pollution meaning a lot of dusted particles there. Basically that particle will be collected to the using this filter paper. Then we can do some lot of analysis. This one this is called a species sampler and maybe high volume sampler. I don't know all of you. It's completely so modeling part. So I just skip it because I don't want to do too much here. We have different industry. Say example Hyderabad, you want or you want the Vizag, Visakhapatnam. So wherever different industries are there, you assume five different industries are there, and you are measuring concentration here. That's mean the instruments we kept here, and you are measuring concentration. So all five industry contributing, how much contribution happening that we can use and we can do some modeling and we can find it what is the one. But problem is if two industries same, like sugar industry, two sugar industries are there, you can see two sugar industries there, then we cannot solve because we don't know which industry polluting. Then of course the same way I already informed, A plus B equal to 1, we cannot solve. So you have to bring one more receptor here and then we can get a clear idea. So which industry polluting that one. I'll skip it and these all little modeling is there. Yes. And again, these are my currently my all output this one. I have 7 PMR of students, sorry, 6 PMR of all are the 70,000 fellowship. Then they're getting 2 lakhs the project also. It is all credit goes to my students because without my students I cannot do. This is a big group from IIT Guwahati. But anyway, this little old photos. And again, it's NIT students and again all IIT students all together. Yeah, I'm almost done. Thank you, Professor Sridevi, madam. Once again, you gave me opportunity to talk here. Thank you. Thank you.
Thank you, sir, for such an insightful and engaging session. Your expertise on water purification technology and lecture comprising absorption in water remediation and significance of nanocomposites in the effective removal of contaminants from water and the modeling of a packed bed reactor and a brief information on microfluidics and ceramic membrane has truly given us a deeper understanding and valuable takeaways. We appreciate the time and efforts you kept into sharing the knowledge with us today. And let's give a huge round of applause to Dr. Sarvarajan and Samiwara for his wonderful contribution.
Yeah, they can ask some questions. Yeah, I mean, please, if they, I mean, not only this one, you can ask even non-technical also, some PhD admission or whatever. Okay, I'm fine. Yeah, please, please, please. If you have any question, they can ask.
I request the students that if any questions are there, they are appreciated. You can ask, sir.
At least one question, some question you can ask.
Questions are appreciated. If you got any doubts, you're free to ask.
That's mean that they know everything. They got full idea.
Thank you, sir, for your contributions, and thank you once again, sir. And we look forward to staying connected and learning more from you in the future.
So, so I'll quit now.
Yes, sir. Thank you once again, sir.
Yeah, thank you, madam. Thank you for Professor Devi, madam. Thank you so much. I'm leaving. Thank you. Yeah.
So good afternoon, sir. Am I audible, sir? Hello. Good afternoon, sir.
Am I audible to you? Am I audible to you?
Yes, sir.
Hello, am I audible to you?
Yes, sir. You're audible, sir.
Yeah. Okay. Can I share the presentation or later? Hello?
Sir, after coming, sir. Sir, after your introduction, sir.
Yeah, okay. Okay.
Now, let's dive. Now, let's dive into another interesting lecture. Imagine walking past an industrial facility and breathing in nothing but fresh, clean air. No foul odors, no harmful emissions, just a sustainable balance between industry and nature. Sounds like a futuristic dream, isn't it? But today, we are here to discuss a technology that is turning this vision into reality. To educate us to the science and real-world applications of this breakthrough technology, we have with us Dr. A. Gangati Garu, a senior principal scientist and head of Department of Energy and Environmental Engineering in CSIR, Indian Institute of Chemical Technology, Hyderabad. He is a distinguished leader in environmental engineering and a pioneer in translational research. With a deep commitment to sustainability, Dr. Rao Garu has made groundbreaking contributions in waste treatment, biomethanation, and renewable energy technologies. I take pride in informing you that he is an alumnus of Department of Chemical Engineering, Andhra University of the batch 1984 to 88. He did his PhD in Environmental Science and Technology from JNU Hyderabad, where he laid the foundation for his remarkable career in research and innovation. He completed his postdoctorate in biofuels from Environmental Research Institute, University College Park, Ireland. Over the years, he has become one of India's foremost scientists in high-rate biomethanation, leading to the development of anaerobic gas lift reactors. His expertise spans multiple domains, including the treatment of solid waste, agricultural biomass, industrial effluents, and gaseous emissions. His contribution to the Bowenpalli biogas plant in Telangana was even recognized by the Honorable Prime Minister of India in Mann Ki Baat address in January 2021. Beyond biomethanation, Dr. Rao has been instrumental in developing innovative waste treatment technologies, including the dry anaerobic digester system, biphasic solid-state anaerobic digester, biofilter technology, and bioslag effluent treatment process, all of which have been successfully implemented in various industries. His work has influenced national and international collaborations, where he continues to serve as a scientific advisor to leading industries and research institutions. In recognition of his pioneering work, he has been honored with prestigious awards such as the Bharat Ratna Sir M. Visvesvaraya Award 2019, IICH Hindustan Dog Believer Award 2014, and Indian Green Energy Award 2019, among many others. As a Fellow of Royal Society of Chemistry, AP Academy of Sciences, BRSI, and the Institute of Engineers, Dr. Rao Garu continues to shape the future of renewable energy and environmental sustainability. Today, we are honored to have him with us to share his insights on abatement of industrial emissions through biofilter technology, a sustainable solution for odor control and VOC removal. Please join me in welcoming Dr. A. Gangati Garu with a huge round of applause. I request you to take over from now, sir.
Yeah. Thank you so much. Thank you so much for your good introduction. And I'm sharing my presentation now. Can you see my screen?
Yes, sir. Yes, sir.
Full screen you can see. Yeah, I'll start. Okay. Thank you once again, Dr. Sridevi and his team and all the students. You spoke wonderfully. You made that introduction. I'm grateful to you, all of you. And in contrast to my own subject, that is anaerobic digestion, bioenergy from organic waste. That is my actually straight. I'm the main subject for me. But I also worked with industrial emissions, actual abatement of industrial emissions through biological methods. So this is also one of my interesting topic. But considering the importance of today's seminar, I thought that I will present this topic. So that's why I'm going through this topic actually. So Dr. Sridev Garu has given me, Professor Sridev Garu has given me a free hand to select the topic. That's why I thought that this is the apt topic for industrialists and other people who are interested there. Even for students also, this topic will be interesting. So abatement of industrial emissions through biofilter, a sustainable technology for water control and VOC removal. So this is the topic today. All of you know that no gases and particulates in the air that are unhealthy for humans, plants, and animals. So this pollution can be in the many form, like solid particles, liquid droplets, or gases. And mainly these gaseous emissions are from industries mostly, and like volatile chemicals, aerosol, and there are other atmosphere reaction products also. Some of the these air pollution problems. So, as I know, total suspended particles, PM10, PM25, these are mainly actually these coal plants and all they measure. Gaseous pollutants, LOX, NO2, CO, O3, lead, volatile organic compounds, greenhouse gases, chlorofluorocarbons. These are the major air pollutants what people consider and which are harmful to the human health, not only the environment but also the human health as well. So mainly, if you look at the industries, all chemical industries, for example, I can name tannery, bulk drink industry, polymer industry, food processing industry, fertilizer industry, and effluent treatment plant, poultry farms, and all. No, you will get a lot of mal waters because these emissions mainly contain not only H2S and ammonia, apart from that, volatile organic compounds. So they are not only malodorous and toxic, corrosive, also adverse effect on occupational health and environment. In fact, the people who are working in the same industry, especially tannery is a very decentralized industry, they also get affected. In bulk drug industry, if you go to bulk drug and pharmaceutical industries also, you can face all these problems. And because of these emissions, so many complaints from public also. So the image of companies also goes down very badly if the emissions are not properly controlled. So that is one of the reason why emissions needs to be controlled from the public perspective, public point of view, public image point of view, and occupational health point of view, and overall health point of the public living around these areas, and environmental benign also, so that this environmental, this like buildings and all gets corroded. So industrial gaseous pollution, for example, as I told you, ammonia, hydrogen, volatile, mainly volatile inorganic compounds. These are the smelling compounds, secularized water causing compound. There are volatile organic compounds also. VOs is what we call generally. And these VOs are amines, sulfur compounds, aromatic compounds, chlorines, volatile fatty acids. Sulfur compounds, I mean even mercaptans also, which are at very, very low concentrations also, they smell heavily. So, like for example, if we have actually collected some emission data in and around some industries, we made one of my student did PhD on biofilters. So that is the reason why today I'm talking about lengthy about this. And for example, tannery, ammonia is around 125 ppm, 80 ppm H2S and VOC 120. Whereas you look at threshold limit values, it is 25 ammonia, 10 H2S and VOC 0.5 to 1. So there are a lot of drastic differences. That's why if you go to tanneries places and all this, tremendously swelling in that area, and people cannot live very happily. So that is the reason why there is always a demand from public that these industries needs to be shifted. So and in this context, we have to control measures are very, very important actually. So impact of pollutants on humans and environment, like all of you know, greenhouse gas effect, ozone depletion, acidification. This acid gases can form acidification and smoke, and eutrophication. Eutrophication in the sense that it will be like, for example, water bodies Because of eutrophication, you form all these weeds and all will get formed, and human health, ecosystem health, and all this. And all of chemical engineers mostly use different techniques for this control of this gaseous pollution from industries. For example, like absorption, and thermal oxidation, catalytic oxidation, selective catalytic reduction, and particulate pollution like spray chamber. For example, this is for mostly coal power plants, spray chamber, cyclone, baghouse, venturi, electrostatic precipitator. So these are some of the equipments are being processed and equipments unit operations being used for the control of emissions in general in industries. So but the advantages, disadvantages of the advantages is that these are all proven technologies. But the disadvantage is that high treatment cost, capital and operating, generation of secondary pollutants. As I told you, if you actually try to control, try to remove gaseous emissions, VOCs and HDS and other compounds, it end up in like acid products. HDS will become acid in liquid effluents. Emissions again, organic compounds, it results in COD in the liquid effluents, and again treatment is required. So that is the reason why actually these several step procedures are required for the treatment of entirely for the zero ZLD. So that is the reason why these technologies are even well proven and very costly, and also these are one of the limitations. One more thing is that we have seen in refineries, for example, I have seen in Kochi refinery. So they have got bitumen dehydration unit, for example. They have got actually catalytic oxidation process actually for the removal of this emissions coming from dehydration. But still around 500 ppm of HDS ammonia VOCs are left out, which are smelling actually. So that is where actually, so these emissions with low concentrations, the suitability of these technologies is very, very poor. So there only this biological method comes into picture, which is emerging as a very good alternative. In fact, actually in European countries and Western countries, it is already a great technology and competing without all compared to the physiochemical methods, and competing with these technologies and taking its own place very rapidly. So in the biological methods also, there are three methods like biofilter, biotrickling filter, and bioscrubber. So in this actually, the advantages is that low treatment cost, sustainable technology, no secondary pollution generation, and highly suitable for tail gases. As I told you, tail gases means which are having low concentrations. So these technologies are really mainly suitable for high volumes of gases and low concentrations having pollutants. These technologies are really very, very efficient and very, very advantageous in contrast to the physiochemical methods. In fact, that's why it is complementary to physiochemical methods also sometimes. So as I told you, so these are all like degrades the contaminants into inoculates less contaminated products, this biological method. For example, the ultimate products are CO2 and H2O. So which are more or less H2O, there is no problem. And CO2, even though it is a greenhouse gases, but to some extent we can all compare to these harmful gases actually. So now this, as I told you, bioscrubber, biotrickling filter, and biofilter, these are the three technologies which are available for this dewateration of gaseous emissions and VOCs removal from the gases. So how to select, like for example, distribution coefficient, what we call in chemical engineering, Henry's coefficient of a compound or mixture of compound needs to be treated determines the system configuration. So means we have to understand the Henry's concentration of particular compound, then only which technology, whether it is a bioscrubber or biofilter or biotrickling filter, then only we can decide which technologies we can select actually. So that decision depends on the Henry's coefficient, which is called distribution coefficient. So in technical characters, if you look at bioscrubber, so maybe I think this I'll explain when I'm just going in bioscrubber. What happens is that this polluted air goes from the typically like a chemical scrubber, it goes to from bottom to top actually. From the top, liquid is and this entire liquid consists of microbial consortia. So when the liquid comes out, there will be separate bioreactor in which this microbial conversion converts this absorbed compounds. Whatever the compounds are absorbed, that gets degraded here, and it goes in the form of CO2 and H2O. CO2 and H2O. If it is sulfur ammonia, it is goes as NH3 and N2. And if it is H2S, it is forms as a thiosulfide, sulfate or sulfite, and sometimes it forms elemental sulfur also, depending on the conditions in the bioscrubber. So it is like typically looks like a chemical scrubber, but microbial consortia will be there instead of chemical. So that is the only difference actually. And very good advantages like operational stability is good, less pressure drop, good control of the biological parameters, less space requirements. But the only limitations is that readily soluble VOCs only we can use, like Henry's coefficient. That is what I told you. Compound with low Henry's coefficients only we can use. So production of sediment sludge, production of wastewater, again treating with bioreactor. These are the disadvantages. That's why people developed another technology called biotrickling filter. In this, what happens? There is a packing bed of materials like a packed bed reactor, and microbial consortia is immobilized on that packed bed material, and it is microbial. When it is liquid, gas goes from bottom to down. Liquid is with very very slow rate, like slow flow rate. That is what trickling it is called. Trickles down from the top and down, and during this process, what happens is that this microbial consortia gets degraded and forms CO2 and respiratory production goes. So, but this is recirculation liquid is continuously necessary, but there is a possibility that the filter can clog because of excess growth of microbial consortia. That is one of the disadvantages actually. And there are very good and synthetic material we have to use packing material. The construction is little costlier than the scrubber, but there are several advantages in contrast to the scrubber. So that is why this is called biotrickling filter. Another, as I told you, biomass accumulation cost, replacing the recirculating liquid frequently, and we have to use blower and pump also. So these are some of the, but despite the fact, these are all proven to be better than bioscrubbers. Now another technology called biofilter. This biofilter, nothing but instead of synthetic bedding material, we use actually organic bedding material, which is naturally available, and microbial consortia is immobilized on that. So the polluted gas goes from bottom to top, and during which this microbial consortia degrades the entire polluted compounds, and the gas before going to the biofilter needs to be humidified, because the bedding material moisture content needs to be well maintained. That is important. And the bedding material also should have all the nutrients. That's why I use it. Naturally occurring organic bedding material should be used. And I will let you know what are the bedding material different and all, what is characteristics and all these things. So as usual, it needs a exhaust fan, blower to let the gas into the biofilter come out. And you can in the soil also, these biofilters could be constructed very easy. On top of it, you can put garden also. Very easy. I have seen several of these biofilters in Europe when I went there. And every chemical industry mostly having these biofilters because when they get low concentration of pollutants with high volumes of gas, high volumes of emissions, these biofilters are proven to be very, very good. And pressure drop is also very, very low. And the bedding material needs to be replaced only every 4 or 5 years. And the bedding material can be directly, it is embedded with microbial consortia and sulfur compounds and organic compounds directly can be used as a soil conditioner. So there is no harmful products in this actually. So the mechanism is that on the filter material, biolayer forms actually, and when the gas flows, the gas which is having initial concentrations of C high, it goes down to C0. That is mean during the process in the biolayer, entire degradation happens actually. So initial concentration of pollution gets down to 0, almost final concentration. Transfer of compounds from gas phase to water phase, that happens in the biolayer. Oxidation of the absorbed compounds by the bacterial space present in the biofilter, that happens in the biolayer. So it is a two-phase consisting of the gas phase to liquid phase to again degradation actually. So biolayer has several loads and biofiltration, aqueous environment for bacterial life, nutrients for biological activity, acts as a water-air interface, acts as a resistant of byproducts of the reaction as well. So much of interesting phenomena is happening. Biofilter looks like very easy, but the interesting phenomena happens over here. So low investment, easy to dispose bedding material, as I told you, low pressure drop, little effluent water, very, very less leachate will come. That easily can be spread back to for improving the moisture content bedding material. So the only thing is that requirement of large surface area, but as I told you, these can be constructed underground as well. So periodic replacement of filter material, that is approximately 3 to 4 years. difficulty of monitoring, and monitoring is not very easy. Humidity and pH of the filter material needs to be maintained, depends upon the efficiency and the concentration variation. Too much of variations, concentrations, for example, if you are designing for around say 500 ppm HDS and ammonia, it cannot allow 1000. So it should be in the range of 5 to 10% only in that 600 to maybe 400 it allow. So those are some of the lists. As I told you, bedding material is very important. Soil mixtures, compost, bark, coconut coir, peat, carbons, mixture of above can be used as a bedding material. And characteristics of medium, correct CBN ratio for bacterial support, that is important. 1:22, 1:50. What water absorption ratio around 40, water retaining capacity, that is called 40 to 60. For example, coconut coir it has got a very good retaining capacity. It's an excellent material for bedding material. So it should offer low pressure depth, there should not be any compaction, and pH control should be there. Actually, should not get acidified very fast. So important operating and design parameters are pH, temperature. Generally, biofilters are operated at ambient temperature, generally in the range of 30 to 40 degrees centigrade. Carbon, nitrogen, phosphorus, and the bedding rate is very important. The important parameters are like, in terms of performance measurement, empty bed residence time, volumetric gas loading rate. 1 second, please. Vijaya. 1 second, please. So, sorry. Empty bed residence time is one of the important parameter performance simulation. Volumetric gas surface loading rate, pollutant mass loading rate, elimination capacity, removal efficiency. These are important parameters. Now to calculate, I will also explain these things to you. So there are so many compounds already proven to be very good biodegradable compounds in biofilter: benzene, toluene, hydrogen sulfide, carbon disulfide, mercaptans, amethyl sulfide, dimethyl disulfide, ammonia, methanol, ethanol, propanol, butanol, aldehydes, butyraldehyde, pyridine, acetone, styrene, xylene, methanol, methylene chloride, diene-trichloromethane, triene-tetrachloroethane, nitrogen oxides, isopentane, ethyl acetate, gasoline diarrhea, VOCs. All these things are proven to be useful. So, selection of biological method, large volumes of emissions with low concentration, as I told you, that is important parameter for selection of biological methods. And cost effectiveness, high treatment efficiency, no secondary waste. These are advantages. And biofilter is one of the best alternative what we can see actually. As I told you, this parameter, for example, empty bed rest times, gas residence time within the biofilter packed bed. So how to calculate this volume of the biofilter divided by volumetric flow rate, and regarding units conversion, it's surface loading rate, the amount of air that is passed to the biofilter per unit surface area per unit time. So that is called surface loading rate. So meters cube per meter square per hour, Q by A, flow rate by area, and mass loading, the amount of pollutant, this amount of pollutant which is introduced into the biofilter per unit volume per unit time. Q, flow rate, volumetric flow rate, multiplied by initial constant divided by volume of the biofilter, that is gram per meter cube per hour, these units. And elimination capacity, the amount of pollutant removed, the amount of pollutant removed per unit volume biofilter per unit time. So elimination capacity, so that is gram per meter cube per hour. Q, that is again volumetric flow rate, within brackets Ci minus CO, that is like amount of pollutant inlet minus outlet, divided by volume of the biofilter. Again, removal efficiency, the fraction of the pollutant removed in a biofilter expressed as a percentage. For example, inlet minus outlet divided by 100 into inlet. So space velocity, velocity of the gas through the biofilter, that is also plays very important roles. And Q by V again. So these are the variety of parameters which needs to be calculated for biofilter, understand the biofilter performance. And we have done a lot of studies in our ISCT for the almost one PhD, almost 2 PhDs completed on this subject actually. So one is Dr. Bharat and another is Dr. Kiran Mani. So we have made experimental setup over here, and 1 meter height bedding material we made. Diameter is 0.04 meter, and like approximately total volume is 1.4 liter. and working mole is 1.2 liter. And ambient temperature we operated this biofilter, and this is experimental setup. And bedding material, I told we used coconut coir with rice husk, wood chips, and polyurethane film. So we used mixed of all these things, coconut coir with rice husk and wood chips. And polyurethane foam is also in between. Actually, we have packed because it is to reduce the pressure drop actually. The idea. So these are the variety of character: bulk volume, moisture content, bulk density, total solids, volatile solids, water holding capacity, CHNS, and NPK. All the parameters we analyzed. So, and we have isolated microbial consortia, and microbial assay was done completely, and nitrogen limiting media, and we have used, and we have used NH3 gas cylinder for towards NHD. Microbial analysis CFE also we did. So batting material, everything is packed. And operating parameters, what did moisture content is very, very important. 55 to 60 and 70 to 2 moisture contents we maintained, which is better like that to understand. And the cylinder, as I told you, used 60 to 10 seconds EBRT. That is one parameter, empty bed resist time. We operated 90 days and inlet concentration in the range of 10 to 220 ppmb. So these were ammonia, and we got a very, very good efficiency, 99%. And so EBRT 20 seconds, that is optimized. MLR, mass loading rate 34, space velocity 178. Ammonia converted to nitrogen gas through simultaneous aerobic nitrification and NMOX process. And operating parameters again for the same HDS biofilter also we did. HDS cylinder we operated with under 10 to 220 ppm we operated. And we got 99%. See, in this biofilter, getting above 99 removal is important, because otherwise the biofilter will be inefficient. We should not have any compound, because threshold limits of ammonia is very, very less. HDS is less, below 10 ppm. So that's why we should not have actually. So if it is 220 ppm inlet concentration, I should have above 99%. Then only it will be, threshold limit will be less. So here, but compared to the nitrogen ammonia biofilter, here EBRT is more, which means residence time is high. So these parameters keep, these are the important parameters which we have to study during the experimentation, so that it will be useful, these design parameters. So HDS is converted into sulfide through sulfur oxidizing process. So that is a mechanism. So we have used triethylamine, another compound, and again same EBRT also we changed, flow rate, everything we changed. And finally, packing material also we used wood chips and rice husk. We keep changed this packing material also. And mechanism is that triethylamine is getting converted into diethylamine, ethylamine, amine, and ammonia through oxidizing biological process. And we got very good reductions there also. Mostly, I think I forgot to put the slide. I think very good, 99% above percentage we got reduction actually. So EBR 20 seconds, and pH everything maintained 7.5. Operating temperature 20 to 30, very like ambient only we maintained. And another thing, ethane thiol, that is mercaptan. We have tried mercaptan, and mercaptan is also very good removal efficiency we got in this actually. Bedding material again, wood chips and rice husk we used, and same moisture content we maintained. This EBRT and all this. So here EBRT is more, 180 seconds. Because of that, whereas in this it is EBRT is 20 seconds. Triethylamine. So here it is 160 seconds. So we operated almost 200 days. Each biofilter was operated almost about 200 minutes. And after completing this pilot scales with this setup, actually whatever the setup I have shown, and we have went for another pilot scale biofilter. That pilot scale, this is the pilot scale biofilter, and this height of the biofilter is almost 1.62 and 1.45 length, and breadth is 1.15, and active volume is 2.45 meter cube. And mixed agriculture acidity we have used in the bedding material, and we have used individual cylinders, atmosphere air for completely controlling the flow rates and all these things, and water tank for water also we have sprayed from the top. This is the one side, you can see the entire picture over here. And wood chips, rice husk, and polyurethane foam, coconut coir and coir pith was used actually in this. And 55 seconds is the ABRT optimized we have put. 220 days we operated the plant between inlet concentration 10 to 225 ppm. And conclusions is that inlet ppm be 210, We got 55 seconds is the ABRT removal efficiency above 95% we got. Present of very low and pH 7.8 and moisture content in the range of around 60%. So based on all these studies, what we did, we designed a full-scale biofilter at a place called Erode. That is a S.A. Abdul Aziz leather industry is there. That is a tannery, and we have designed a full-scale biofilter. You can see in this drum yard section. This is the left side top, right side top diagram. That is the drum yard section where leathers are actually in the drum yards. No, they'll put drums. They'll put it and circulate, rotate it continuously by adding different compounds, ammonia compounds and sulfur compounds and all. So very lot of water comes from this entire this drum yard section. People cannot just stay for even for 1 minute also, but their workers are working because they are habituated and because that is their livelihood also. That is why even the occupational health is there, they are working. So what we did, we have fixed 3 exhaust blowers from this section. Entirely the gas was taken out. Whatever the malwater gas was taken out and put it to the biofilter. You can see the left side biofilter. You can see the structure. 3 biofilters we have put. From 3 exhaust fans, we connected to 3 biofilters. And when the gas is passing out, there is no smell at all. So what happened? That's why fresh air was always coming to the drum yard section. Whatever the contaminated is getting purified in these biofilters. So this biofilter is operating will not below more than almost 8 years now. This is operating continuously. Only in between we changed the biofiltering bedding material. This so where places we analyzed using different probes and all, analyzed H2S and ammonia, VOC compounds. And the parameters are flow rates 442, that is meter cube per, that is nothing but 260 CFM, and volume is 13.5, and inlet concentration 90 to 100, H2S, ammonia 80 to 120, and empty bed resistance 60 seconds we have used, moisture can 55, 60, and entire all this, how you looking top and all, how you are spraying the water, you can see from these figures actually. So 100% efficiency we got it. So the workers are so happy and delighted actually. So one of my PhD students stayed almost 6 months there and operated the biofilter to see any performance and all these things. It has got a lot of control units also, like as I told you, whatever the gas going to the biofilter should be humidified, and actually temperature also we should monitor, and we should keep supplying nutrients. Any deficiency is there, whatever leachate is coming, we'll analyze for HNP, and the leachate and any nutrient deficiency are there, nutrient elevation should be dosed actually. We have made a central control unit also to all these things, and whatever the exhaust gas means, every day needs to be analyzed using the GC or whatever the method. Suitable methods for HDS, ammonia, different methods, and all organic compounds with GC. And performance on full scale, you can see this. No, this is actually 30 months old I have taken. Now, as I told you, almost 8 years it is operating actually. Only first 30 months when our PhD student, that is the data I am showing to you. But now it is almost 8 years we completed, and we have got a very, very good results on this. And people, they are very, very happy. In fact, the government of Tamil Nadu want to actually at the time, they're ready to promulgate a law saying that every tannery should have this biofilter. But somehow that could not happen. So this is the nutshell of whole pilot plant and all these things, lab scale and pilot scale, full scale. I can make conclusions with this table actually. We have got different, like, this empty bed resistance is one of the important parameter, varies from compound to compound. That is the important design factor. It should be understood very well. And removal efficiency we have to measure. And continuously, biofilter need to be operated for longer durations. So that's why operated for almost minimum 3 months to almost 1200 days. Is I think 8 years plus actually. So then only the performance evaluation can be made. Otherwise, it is not possible. So the technology developed by biofilter IICT, it is very low cost technology, environmentally benign, easily installation and operation. Purification emission at source, it happens actually, and very, very easy to. For example, you will be surprised, the biofilter which we have constructed at this place, this biofilter costed us only 8 lakhs rupees. 8 lakhs rupees, such a lot of benefits actually. So, and apart from after that biofilter, we have also installed, there is a Fleming Laboratories bulk drug unit in Hyderabad. We installed also there. We are about to install at common effluent treatment plant Vijayawada, but somehow they backed out. They're actually, I think CETP is closed now, it's not working. That's why they stopped, even though they have given order to us actually. So this biofilter is in nutshell, what I can say is that very good technology for emissions control, for VOC removal and water control, especially for low emissions. For example, the low concentration of compounds and high volumes, the biofilter is very good for chemical industry. I think one should, I think students also should keep working in this area. Researchers also think about this, so that we can give advice to so many industries. Now, most of the industries, when I'm like as a member of this pollution control board, when I'm like task force member, CF member, I'm observing most of the people don't know about these biofilters actually. So that is the irony of it, and we have to explain the chemical engineers. I think we need to propagate it and educate them and design these biofilters which are very cheap and cost effective. Thank you once again for giving me this opportunity.
What an informational and insightful session we just have experienced. We sincerely thank you, sir, for sharing your invaluable knowledge on biophysical technology. Your in-depth discussion on sources and effects of air pollution, physical, chemical, and biological cleanup mechanisms, especially the biotechnological solutions like bioscrubber, biofitting filter, biofilter technologies, has given us a fresh perspective. And thank you once again, sir. We eagerly look forward to future interactions and gaining more wisdom from your expertise, sir. Thank you, sir.
So thank you so much, all of you. Thank you, Dr. Sridevi Garu, Professor King, Dr. Naidu, everybody. And thank you all the team, young students. You are organizing very nicely. I could have come personally. They were there, I think. I could see very colorful dias and all these things. So grateful to you. And can I leave the meeting now?
Yes, sir. Yes, sir.
Thank you, sir.
Thank you so much.
As we near the conclusion of this insightful and enriching conference, it is time to express our gratitude.
Every evening to one and all, it gives me immense pleasure to deliver the word of thanks of this workshop to all the dignitaries and participants assembled here. Firstly, I would like to thank our Honorary Vice Chancellor, G.P. Rajashekar Garu, Rector, T. Kishore Babu Garu, Principal, Satibhushan Rao Garu, Registrar, Dhanjay Rao Garu, and the Head of the Department of Chemical Engineering, Professor G. M. J. Raju Garu, who have given permission, encouragement, and support to organize this program. I would like to thank our Chief Guest, who honored this event with his inspirational thoughts. I would like to extend heartfelt gratitude to our guest of honor, Dr. P. Srinivasa Rao Garu, for gracing us with his presence today. On behalf of our organization, I would like to extend our heartfelt gratitude to the President of Workshop for his exceptional leadership. On behalf of the entire workshop organizing team, I would like to extend our deepest gratitude to our co-chairman of this workshop, Professor Tripati Kingaru, for his invaluable contributions and unwavering dedication that made this workshop a resounding success. On behalf of all the participants, I would like to extend our heartfelt gratitude to the organizing committee for their incredible dedication and hard work in making this event a great success. I would like to extend our deepest gratitude to the esteemed sponsors, Professor GJV Jagannath Foundation, Civis Laboratories Limited, Visakhapatnam, Ramanamurthy Garu from Sri Vriksha Junior College, Kamalu Garu from HPCL, whose generous support played pivotal role in making this event a great success. And we are truly appreciative of your contribution to this impactful event. I deeply express my sincere gratitude to the faculty members of the Department of Chemical Engineering and colleagues of other departments who generously contributed their expertise and time to make this workshop a overwhelming success. I would like to express my grateful gratitude to the students, volunteers, and participants who made this event a grand success. I deeply express my sincere gratitude to the non-teaching staff computer center staff, catering services, and other outsourcing support who have done their tireless work and dedicated support to run these workshops smoothly. Once again, I express my heartfelt thanks to the speakers, organizers, and anyone who contributed directly and indirectly to run this workshop peacefully, successfully, and have a wonderful day. Thanking you, one and all. Thank you.
As we move towards the final moments of our event, I request everyone to rise for the national anthem as a mark of respect for our nation.
సౌండ్ అందరు కలిపా
उच्चल जलधिकरन्दा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जयकारा जय गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे जय हिंद.
We express our immense gratitude to all the organizers, volunteers, guests, and the students from different universities for taking part and making this event a grand success. With this, we conclude today's highly informative workshop, and I request everyone to enjoy the refreshments provided outside the auditorium. Thank you.